Thank you. Good morning, everybody. So thank you for picking it up this early. So I'm really excited to be here and talk to you guys about my work with on CMB delensing. And part of the excitement is that, in fact, this is basically the first time that any of this is getting presented. And there's a forthcoming paper that you should look for in next week after that or so. And this is in collaboration with these two guys, Ethan Andrews, who's actually a statistician at UC Davis. It turns out statisticians know a lot about Gaussian random fields, which ends up being kind of important for us. And with Ben, who was here earlier this week, and maybe you saw his talk. But, so the question that motivates us really for this work is the following, and it's how do we optimally delens future CMB data so that we can get the best possible estimates on R. So I think I've been given really great, backup information, prior information by all the great talks at this conference on this question. So I won't really go much into the background, but I will skip right to something that is usually good to do, and I'll write down the answer to that. And I think the answer basically is this. This will be kind of central to the talk, and this is the Bayesian posterior probability of F, phi, and R. So F was the CMB fields, which is like a tuple of temperature and polarization, Stokes parameters, the lensing potential, some cosmological parameters like R, and all of this given data. And pretty much, I think, this is in some way like the holy grail of CMB delensing, which if you know me, you know would be represented in my head by a six-pack of beer, Holy Ale. And I say it's the Holy Grail because well, if you had this, then you could maximize it and you can get the best fit values of these parameters. If you had samples from this probability distribution, you could quantify uncertainties. And in fact, this is what we're after in this talk. And what I'll talk about really is figuring out a way to maximize this. And that's the work that we've done, and I think we feel like we've succeeded in doing. And I'll give you a preview of drawing samples from this probability distribution, and that's sort of more ongoing work. So we have a couple of other things in the toolbox that already exist. So one is a quadratic estimator. And so this is just a weighted sum over different quadratic combinations of the data. And so basically all current analyses are based on using this on data. Currently it's great, it's near optimal. In the future, as we've heard, it will become suboptimal once we get to lower noise levels. And we want to push past this, and there's factors of 2, maybe 3 in terms of shrinking the error bar on R that could be had by doing something better than this if we assume noise levels of something like CMBS4. You can think of this guy, in fact, by the way, as basically if you start at a particular point in parameter space of the main guy and you take one single gradient descent step, and then that in some way basically is the quadratic estimate. And so that makes clear maybe why it's suboptimal. It's because we just took one step, and so we're not actually at the minimum yet. So we can, and others have tried obviously to improve this optimality. And another thing that exists are algorithms that are actually based on this guy, which is the marginalized probability distribution on just phi now. And so literally this is just taking this and marginalizing out the field. And then at least really in their stated form, these two works kind of take R as a fixed parameter, and there's maybe ways, I think it's ongoing work how that might turn into something which you then actually estimate. So both of these works are really important improvements to the optimality of phi. But in terms of the original problem, there's a couple of issues. So one is this fact that R is really taken as given for saying these works, and the other is that the unlensed field here is not really estimated, right? It's actually explicitly marginalized out in this likelihood. So, while these works give you the maximum of phi, it's less clear how you use that to get optimal delensed map or even to estimate R. So, why is this problem that we've chosen to tackle sort of hard? Why hasn't it been done before? And well, one of the reasons is just that, well, it's more variables we're trying to estimate. It's higher dimensionality, right? We're trying to estimate all the pixels. So there's now, T, Q, and U pixels that we're estimating in addition to phi. And beyond that, though, there's also this fact, and that is that it's actually a quite correlated problem. So the unlensed field is quite correlated with phi, and you can understand that just by simply, if the data tells me that there's a hot spot here, that could either be a hot spot and no lensing, or it could be a hot spot over here, which was lensed to over here, and so there's a degeneracy. And you can get away from that if you do a reparameterization, and you instead look at the lensed field, and now your data just tells you, up to the noise, this is what the lensed field is here, and there's no degeneracy with phi. And so if you're in a parameter space that looks like this, it's easier for the sampler maximizer to navigate it, and so on. So this was pointed out by Ethan and collaborators in 2015, in fact. And so what you want to do is you want to take this probability distribution and just use the lens parameterization instead. And so you just do a change of variables here, but actually that introduces this determinant of a Jacobian matrix that you get from this change of variables. So, there's a saying, there's no such thing as free beer, someone's paying for it. And so this is where we paid for it right here. Because now this determinant is, in fact, lensing is this linear operator that relates the unlensed and lensed fields. And so this is the determinant of the lensing operation that appears in there. It depends on phi, and so nominally you think you have to calculate it if you want to use this form. So, actually, let me backtrack for a second. What does the determinant of lensing mean? I think probably most people haven't thought about this too much because it doesn't come up maybe except for these Bayesian sort of frameworks. What I mean by determinant of lensing is simply lensing is a linear operator, and so it's got some matrix representation and determinant of that matrix. On the infinite resolution, where lensing is basically just a permutation of pixels, this would by definition basically be 1. But on pixelized maps, actually it doesn't have to be 1. And I don't have a good argument as to what it should be or how to calculate it, but I've just gone and done it brute force for at least one particular approximation to lensing that's used, and that's this Taylor series approximation. And here we just have basically, so we know that the lensed field at some position is the unlensed field displaced by some small gradient of a lensing potential phi. And so then we just Taylor expand that in phi, and you have the 0th, 1st, 2nd, and so on order terms. This guy here is the lensing operator itself. And by virtue that you could just calculate this, you could stick in impulse responses and actually explicitly build this matrix. And you can do it for really small pixel maps, otherwise this gets totally huge. But here I've just done it, and so for some random phi that I sampled, it looks like this. Kind of like what you might expect, the E and B are coupled, and it's kind of identity. Ultimately, I just go and I take the determinant of this matrix, and I get this value, which is, so it's not close to 1. In fact, it's really close to 0. And maybe more importantly, and I won't go into that here, but if I look at for different values of phi, what this determinant is, it actually changes a lot. So this is not a constant that I can just ignore in the probability. This is actually something that I would seemingly have to calculate. And so that might sound like a roadblock, but actually what we found in this exercise was a solution. And that solution is this algorithm that I'm going to describe now called lens flow, which is a brand new way to actually lens a map. So it's a different approximation to pixelized lensing than some of the other things that exist, and by construction, actually, it will have determinant 1. And it's pretty cool how this works. It's quite simple. And basically, you just take this lens form here, and you add some arbitrary parameter, which we call time for some reason, and when you do this, then you know that at time equals 0, this is just the unlensed field, and then at time equals 1, this is the lensed field. And then it turns out that this time parameterized field here, actually you can show it obeys a differential equation, an ODE, a flow equation. The flow means that it's just one big operator here, which just hits the field itself. Also importantly, all of these things are only evaluated not on any displaced pixels, they're just evaluated on this initial x. And so, by virtue that you have this now, you can actually do lensing in the following way. So if I want to lens a map, I stick an unlensed map as the initial conditions, and then I just run the ODE. One thing that's pretty amazing is now to just delens a map, I actually just run that ODE backwards. And so I get exact inverse lensing for the exact same price and conceptually in a quite clear way by doing lensing in this fashion. And I won't have time to go through the proof, but you can actually just provably show that in this form you get a determinant equal to 1. And it basically has to do with the fact that this velocity operator here is antisymmetric. So by the way, in practice, so we do this algorithm and we solve it with fourth order Runge kata with seven time series steps, and it works fine numerically. It's fine, and so this is great. We now can do that lens parameterization. So let me show it to you in action a little bit. So this is a zoom in on a super small patch of sky, so you can really see some pixels, because this is what matters, right? Pixelization. So this is a phi that I've simulated, and this is a field some temperature field that I've also simulated and lensed by that phi. I don't actually remember if I did the lens flow or Taylor series ones. You wouldn't be able to tell. But the difference between doing this lensing with this new lens flow algorithm or with the Taylor series thing is shown here. And so, right, so this scale is a couple orders of magnitude below this, and there's differences. And you know, these kind of look like numerical artifacts, but they're really not. They're actually the real difference between how these two algorithms basically extrapolate down to the sub-pixel scale. And they're why the Taylor series thing gave me the zero-ish determinant, whereas this new thing can give me exactly 1, basically up to ODE integration errors. All right, so now I've got this tool in the toolbox, and so let's do maximization. So because you basically now think that you have this fairly uncorrelated parameter space, one thing that would make sense is doing something like a coordinate descent. So you just step in the lens field, you step in phi, you alternate, and this is indeed what we do. And there's actually another really great reason that this lens parameterization is kind of fundamentally really useful for this problem. And for that, let me actually write down this posterior for the first time in this talk. And there's basically 3 terms. There's a likelihood where you just compare data to the model, the lensed field, with respect to the noise covariance. And then there's a prior on the unlensed field. That's just the CMB power spectra that you stick in. And then similarly a prior on phi. And so now if you think about the step in the f tilde, there's no f tilde in this term. So that's actually just these 2 terms. And maximizing those 2 terms, if you're familiar with these things, you'll recognize that as actually just a Wiener filter. And so that's great because that's a super well-known problem. We have lots of tools, lots of ways to solve that. And we've taken this bigger joint maximization problem and broken off a really clean piece of it into this Wiener filter. Similarly, there's the phi step. Now here, this doesn't involve this term. There's no exact solution. There's no like Wiener filter thing. We actually in practice just do it iteratively. But there's also a really nice thing here, which is that this maximizing these 2 terms doesn't involve the instrument at all. So the instrument comes in as the noise covariance, the data, masking, any of this type of stuff would be in here. So the phi step is actually totally independent of that. And if you had used the unlensed parameter, then phi dependence would be in the likelihood term, and this nice separation would be present. So let's see this maximization in action. So I've just simulated some data with some 1 micro-K arc minute noise, a fiducial R that I stuck in there. The only thing you have to specify basically is a starting point for phi, and you can do 0. It's fine. So the maximization is in the lensed parameters, but I can of course just go look at the unlensed parameters at any point throughout this maximization. So here's the very first unlensed B estimate, which is terrible because my current phi estimate is 0. But I sort of iterate, and I get a first phi estimate that delenses the data, which gives me a better unlensed B estimate, which in turn, and so on and so forth. And I kind of get to the end here, and I get something that looks like unlensed B and phi. And so if you keep those in mind for a second. By the way, I skipped a few steps. This was 30 steps of this algorithm. I get to something that looks a lot like the truth. So what you're looking for here is basically, does this look like a Wiener filter solution? And it does. It's sort of smoothed out on small scales and tracks the truth really well. This was 30 minutes on one single CPU, by the way. An important thing for real analyses is masking. And basically this works too. Like I said, there was this really nice feature that if in the lens parameters, and the masking only changed the Wiener filter step. And so it just amounts to basically you have to let that run longer. What you get, so this masking here, you can probably tell, right? I put a border around this patch here, and it looks like you might expect. Here's what the phi estimate looks like. And this is a bit, it doesn't seem to visually match, but actually if I look at the convergence, so basically the magnification, and compare that to the truth, actually it matches basically exactly. And what you were seeing before there is essentially a mean field. Now, if I was going to try to use this procedure to build an estimator, I basically would have to compute that mean field and subtract it out, or something like that. Of course, that's not what I'm doing here. I want to do this maximization so I can get to the peak, and then I can do samples from this probability distribution. And essentially, in the process of doing those samples, I will be removing the mean field, because marginalizing over the other parameters effectively will remove it. But the nice thing is that it's really conceptually clear how I should do those simulations. So a problem with things like the quadratic estimate is that you debias it with simulations that assume some value of, say, R. Whereas here, during these samples that I will do, there's no, it's totally clear what value of R I take, right? It's the value such that I'm sampling that posterior probability, so it's really clear. And so then, let me come back to the initial problem at hand in my final slide. What about R? So I don't have the full example to show you. Most of the work was really validating and making this maximization procedure work and the related lens flow. But I do have a simplified example to show you, and that's where I've actually fixed phi by sample from F and R. And those sampling, which is done by Gibbs sampling, in fact, look exactly like they will look in the final algorithm. So the only difference is fixing phi. And so basically the point here is just that, for the fiducial value that I've put in for R, I get some distribution of samples from this Gibbs chain. I get an associated set for each of the R samples. There's a unlensed map that comes out, which you see here. And I've picked 3, which in the chain happen to have a small, medium, and large value of R. And so this is also really nice in terms of an analysis perspective, because a byproduct of this analysis is a set of these maps. And so then if you want to do something like, say, a cross-correlation analysis, what you might do is just take that external tracer that you want to cross-correlate and just cross-correlate it with each one of these samples. And if you can rule out some of these samples, then that immediately turns into better constraints on R. And it's kind of a nice way to fold in these external data sets. So, to conclude, let me just say that I think we've figured out how we can maximize this joint posterior probability. We can do sampling, and I just gave you sort of a preview of it. Look for our paper in the next weeks or so. And I'm looking forward to more improvement. We're working on application to data, and this was the first time this has ever been presented, so I'm curious to get feedback. Thanks.